Okay, so let's get started. Can everyone hear me? There was somebody said that they couldn't hear in the back. It is kind of soft. Okay, I will speak up, but I'll also see if they can do something with the AV. Well, there is no AV. They have to put in a AV. We'll try to figure that out. Okay, but if you cannot hear me, just please raise your hand and tell me. I would rather not have you sit there and not understand what's going on. All right. So today we are going to talk about system and kernel calls, and also I will introduce the first real lab assignment, okay, which will be given to you later this afternoon. Okay. So we'll talk about system calls more generally. Okay, that's something you probably have seen in a undergrad OS class somewhere, but I'm going to do a quick refresher so everyone is on the same page in some sense, and then we will look at system call in Minix. Okay, we'll talk about kernel calls in Minix. We talked about this a little bit already, okay, and then I will introduce the lab assignment and what you're supposed to do and what not. All right. So let's start with system calls. Okay, as I've already mentioned, okay, this is the interface that the OS essentially exports to user programs. Okay. Even though it's the interface for users to interact with the OS, typically users don't program at a system call level. Okay. When you write your code in Python or Java or even C or C++ for that matter, you are programming to a library interface. Okay. There is a higher level interface that's exposed by libraries, and those libraries in turn actually use system calls to implement whatever functionality they are exposing. Okay. So some common APIs for libraries are the POSIX API. For on a Unix platform you are programming in C or C++, you are using the POSIX API, okay, and I'll talk a little bit about that today. So most flavors of Unix, which includes Linux and Minix, essentially implement a POSIX API. Okay. If you are coding in Java, you essentially have the JVM interface. Okay, that's the Java interface. You're programming to that. Okay, and then if you are on Windows, you have the Win32 APIs and so on. And of course, if you have code in Python, there are lots of libraries that sit even above those APIs. So you may be programming at an even higher level of abstraction. Okay. So that's something to keep in mind. So most likely, even though you've written lots of code already, you really haven't even directly invoked a system call yet. Okay. But you've written code that is indirectly invoking system calls. All right. So now we got to understand system calls in more detail, because you are going to implement one. You are not going to invoke one, but rather implement one yourself. Right. So here is the picture of what I showed you, or not what I showed you, what I spoke about. Okay. So there you have at the top a user program. It's written in C, so you understand how things work. So it's basically calling printf. It's essentially supposed to print a string on the terminal. Okay. So when you call printf, you essentially go to the standard C library. That's where the printf function is implemented. Okay. Now printf, the implementation of printf is in turn going to call a system call. In this case, you are essentially going to call the write system call, which takes that string and writes it out to a console. Okay. So that's typically how you should expect system calls get invoked. That's essentially what I said on the previous slide. Okay. So what we want to understand is actually the bottom part. Okay. You know how to write user level code. You want to understand what is actually happening when write gets invoked via some user level program, okay, or any other system call for that matter. Okay. Same concept in Windows, nothing has changed. All the function names are different, system call interface is different, but essentially they do the same thing. I'm not going to go into the details. This is just a Windows function. It's called read file. I expect you understand what it is going to do. Okay. So it's going to read data from a file. All right. So this is again somewhat of a refresher from undergrad OS. So as you may recall, if you still recall that material, when you call a system call, it's going to invoke a trap. Okay. Trap is a software interrupt. Okay. I'm going to show you a picture in just a moment. Okay. So that trap essentially causes the kernel to start executing. Okay. So now, because system calls are implemented inside the kernel, Okay, it is the interface that the OS is providing. So, essentially the code for the system call is inside the kernel. That is not true for Unix, as we will Minix, as we will get to, because in Minix system calls are essentially implemented by system processes, not inside the kernel. This is a generic explanation of system calls. It assumes a monolithic kernel. Okay. So, essentially when you invoke a system call, it causes a trap, which is a software interrupt. The software interrupt essentially invokes the kernel. Okay, the kernel is going to start executing. It is going to essentially index into a trap vector. Okay, if you will go back to lecture 2, I was talking about hardware features. I briefly introduced this notion of a trap vector. It is essentially a table. Okay, every system call has a unique number, as we will see. So, to implement a new system call, you got to actually identify an unused number in the system call table and use it. Okay. Essentially, what this table has is it is a set of addresses which tell you where in the kernel that system call code resides. Okay. So, if you call system call number 15, you are going to look at the 15th entry, okay, in the table that will have an address. Then you will essentially index that address and go to that memory location in the kernel, start executing the system call. That is essentially, I am going to show you a picture here. So, that picture essentially shows you what I said. Okay, here we have a system call, go to the syscall interface that causes a trap. Okay, the trap will cause the kernel to execute, and in doing so you have to remember you switched from user mode to kernel mode. Okay. The CPU bit has flipped, you are executing in kernel mode. Okay. In user mode, certain things are not allowed as far as the CPU is concerned, the hardware is concerned. In kernel mode, anything is allowed. Okay. Anything that the kernel wants to do is allowed. So, here you have, let us say the system call ID is I or n. You look at the nth entry, that basically points you to the function within the kernel where that system call is implemented. You go there, you execute it, you return the results. Okay. Is that clear? Any questions here? Okay. This is something that is somewhat of a refresher, but you should understand. Okay. So, a few things to keep in mind. Okay, there is a unique number, integer associated with every system call. They have to be unique because there is one entry in that table, okay, corresponding to each system call. Okay, that is why you have those numbers. Okay. As far as the user is concerned, they do not really need to know this is happening under the hood. You call printf or you call some Python code or Java code. Okay, you are just wanting that function to execute. You do not actually care whether it invokes a system call or not, but under the hoods, this is essentially what is happening. Okay. All right. So, now a few things to keep in mind. Okay. How do you pass arguments to a system call? Okay. This is going to be somewhat different from how you pass argument to a function. Okay. Suppose you wrote some code, okay, you called a function, you pass some arguments. Okay. How does the execution of that function work? How do the arguments get passed to that function? Yes. Okay, so you are going to use a stack. Okay, when you call that function, you essentially push the arguments onto the stack. Okay, that is how any code works. You should know all this. Okay. And then you are going to look for those variables on the stack, and the return value also is going to come back to you from the stack. Okay. Now, this may or may not work when you call a system call. Okay, let us first think about why it may not work, and then I will say a few things why it could be made to work. Okay, why would you not want to push something onto the stack and then invoke the system call? It is a function after all. Why do you care? Why does the OS care? Yes. Okay. So, the OS is an independent address space from the user process. Okay. Think of OS being one process and the user process being another process. So, if you push arguments onto the stack of that user process and then you cause a trap, the kernel starts executing, the kernel has its own stack and whatnot. Okay. So, that mechanism where you push something onto the stack does not quite work as is, because you are talking about two different address spaces. Okay. So, typically operating systems will use other mechanisms to pass arguments. Okay. What could you use to pass information between two processes? Yes.
Registers.
Okay, so you have to use something that is independent of that process address space. Okay, so you could use registers. It actually says that there, right? So you can, so many system calls are simply going to push the arguments onto the register, do a trap, and then the OS is just going to pull the arguments onto a register. Okay, a simple method to pass argument. Okay, now if the arguments are not necessarily integers and things of that sort that fit in registers, you need a different mechanism. Okay, where else can you keep data? Okay, the answer is still there. Okay, you can put it on a memory block. Okay, if you can't hold something in a register, you create a piece of memory that's not necessarily on your stack, mind you. Okay, you essentially create a block of memory, put all your arguments in there, and then you got to pass that address, physical address of that memory region. Okay, so you could do that. You could, okay, also still try to use the stack method, but in that case the OS needs to know what process it was that invoked it and go and look for the information in the right place. Okay, so long as you can do that, okay, you could do it, but by and large we have to remember that you have to do extra work. Okay, when you are executing a function, the stack is already there, you can pop it up, pop off the arguments here. That's not going to be the case even if you use the stack. So argument or parameter passing requires a little bit of extra work when you implement a system call. Okay, is this clear? Okay. So with that background, let's talk a little bit about Minix and things of that sort. So let's just go back to POSIX. Okay, POSIX is essentially a standard that is implemented by the IEEE. Essentially, it's a set of API calls that are defined and said any OS that implements that API is going to be called POSIX compliant. Okay, it basically complies with that standard. Okay, so and the reason for this is portability. Okay, because there are many different flavors of operating systems. If you write your code to work on one operating system, okay, typically if you try to recompile it on another OS, it may not work because the interfaces on that OS may be different. Okay, but if that OS supports the POSIX interface, okay, you should just be able to recompile and your code should work. Okay, so that's the reason they decided to standardize the interface. Okay, this came about because there were many different flavors of Unix. Okay, IBM had its own commercial Unix, and so did every vendor of Unix, and then there was Linux and there was FreeBSD. They all looked like Unix, but each of them had their own interface. Okay, you couldn't write code on one machine and then expect it to work on another OS platform unless you change some things in your code. Okay, that doesn't quite scale from a portability standpoint. So POSIX standard essentially tries to address that issue. Okay, many OS platforms implement a POSIX interface. There's even a POSIX interface on Windows. Okay, the Windows native API is not POSIX; they have their own API, but they have a POSIX layer. So you can take POSIX code and actually get it to run even on Windows. Okay, so you have to recompile the code, but other than that, it should work. Okay, so it's an API that is adopted by many different OS platforms. Okay, some examples of what you can do with that API. These are not system calls, mind you. Okay, some of them will be system calls, but they don't have to be. This is just an interface that application programs can use. Okay, some of them require that you also implement a system call with that, but that's not necessary. Okay, so there are lots of networking calls for socket communication. That's the lowest level of network communication you can use. There are all kinds of things for file I/O. All of threads that you implement on Unix platforms uses something called pthreads, which stands for POSIX threads. So all the threading APIs are common if you use POSIX threads or pthreads and so on. Okay. Now there's a link there. If you're interested in looking at the POSIX API, you can go and take a look. Okay, we don't need to go too much into POSIX calls because they're not really necessarily system calls, but I just want you to know that these calls exist because Minix also supports a POSIX API. Okay, as we will see in just a moment. Okay, so now just have this picture in mind. This is what I showed you maybe 2 classes ago, or maybe even in the last class. So that's our Minix picture. Okay, you have multiple layers. There's a microkernel at the bottom. Okay, there are all kinds of system processes. okay, that implement OS functionality, and there are user processes. Okay. So, as far as Minix is concerned, okay, this dotted line here is where you actually see a POSIX API. So, all user programs see a POSIX API. Lot of that API is implemented by these processes, okay, not necessarily by the kernel, but the system processes actually implement that POSIX API. Okay, and then we will see what the kernel does for us. Okay. So, the system calls in Minix are also implemented at that same layer, okay, that I mentioned, okay, because last time if you remember I said that in Minix there is a difference between system calls and kernel calls. Kernel calls are the interface that the microkernel implements. Okay. The microkernel, remember, is very compact and small. It does not implement all the functionality that a monolithic OS implements. Okay. So, the kernel calls are going to be a subset of what you actually can see at the top layer. Okay. So, there are some kernel calls, but these processes will implement additional functionality, and that is where you will have the system call interface. Okay. Is that clear what I just said? Okay. All right. So, these are some system calls. Again, we will, when we get to each OS component, we are going to look at these in more detail. Okay. There will be process management interfaces to do things like fork and wait and exec and kill and whatnot. There will be timing APIs that the system calls implement. There will be a lot of file management calls, open, close, read, write, everything to deal with directory management. All of these are going to be system calls. Okay. So, these calls are now implemented by either the process server or the file server or some other server, okay, that is implemented in user space. Okay. So, if you want to look at the system calls that are implemented, there is a file that I listed there, okay, that is going to show you all the calls that are implemented in Minix. You probably can't read this, but I have it on the Minix source code somewhere. Okay, here, maybe you can't read that either. I can make that bigger. Okay. So, you will see that every system call that you define is here, and it has a number associated with it. Okay. That number is the number you are going to use to index into your trap vector. Okay. So, the reason I mentioned this is you are going to go modify that file when you implement your own system call. Yes, question.
How to decide whether to implement some functionality as a system call or as a function?
Okay. Question is, how do you decide whether to implement some functionality as a system call or a library function? Okay. Is that your question? All right. So, typically if you can do something in user space, you are not going to call kernel services, right. So, you are going to implement a library function. So, let us say you implement a square root function. Okay. You have math library. Okay. You have a square root function. There is no reason to call a kernel call to do that, right. So, you can just essentially call some math operations and implement that function. Okay. So, the reason you are going to make system calls is you want to essentially invoke OS services. Okay. Some things, as we had mentioned, can only be done by the OS. Okay. Like file IO is protected. You cannot just do file IO without the OS helping you do those IO. So, those are things you will actually implement as system calls. By and large, most things are not going to be implemented as system call. You will implement them as libraries or direct user level code. You do not actually need the OS to help you do anything. Okay. So, that is something you want to keep in mind. Any other questions here? Yes.
Kind of specific to this, but is there any rhyme or reason for n calls being defined as 114? Is that how many they've defined?
Okay. So, yeah. So, there is a number of system calls, which basically says that if you scroll down, you will see that says n 113 is where it ends, and there are some special ones that get later numbers. So, that is the number of calls that are supported in Minix, or this is version 3.2 of Minix. You will see the number changes with, you can have extensions as well, but yes, that is why it is that. Okay. All right. So, we will come back to this file in a minute, a few minutes, not a minute. Okay. So, there is essentially that functionality that you define there. Okay. Now, if you remember, I already mentioned that things like device driver, OS components run in user space. So, the implementation of system call is not exactly the same as you would implement it in Linux. Okay. So, you will essentially implement a system call entirely in one of these processes, okay, or using a combination of some code in that process and code in the kernel, depending on what the system call actually needs. Okay, some things can be implemented directly in one of those processes. So and we will see there are different kinds of system calls that might do one or the other. Okay. So the important thing is the user process cannot directly make any kernel calls. I think I mentioned that already. Okay, user processes only talk to OS system calls. The system processes are the one that might invoke kernel calls as needed. So there is that difference between kernel call and system call that is somewhat unique to Minix. You will not see this distinction in Linux. In Linux, if you ask some OS programmer system call, kernel call, they will say it is the same thing. Okay. In Minix, it is not the same thing. Okay. That is something you want to keep in mind. All right. Okay. So the implementation of system call is not very different in Minix from the general implementation I spoke about. Okay. So when you make a system call, okay, you are still going to have a trap, okay, you are still going to pass some arguments, okay, except that your call is now going to go to one of the system process. It is not going to go directly to the kernel. Okay. That is the main difference. In a OS like Linux, make a system call, you have a trap, it goes directly to the kernel. Here is going to be handled by one of the user level process, system process. Okay, and that system process will then decide whether it can implement all of its code in that process or it is going to go to a kernel to ask for some additional help from the kernel. Okay. Now, there are some things you need to know, okay, where all these things reside in the Minix world. Okay, system calls are essentially going to be in this, I will show you, it may be easier. Okay. So, if you go into Minix kernel system, you will see there is one file for each of those calls that I showed you in the previous file. Okay. So, this is the ID of each of those system calls, this is the implementation of each of the system call. Okay. So, there is one file per system call, that is where the code for that system call resides. Okay, so, if you want to implement one, you will have to go there and put one, okay, create a file and add some code to do that. Okay, so, that is the first thing. Okay. So, now just to understand, we will take one system call which is fork and just walk through some steps. Some of the lower level details typically you do not need to worry about if you are adding a new system call, but you need to know what the execution trace of that system call looks like. Okay, so, we call fork, a trap occurs, goes to the process management server or the PM, okay, and so fork is system call number 2. Okay, so, you are going to index into the second entry, okay, and essentially start executing. Okay, as I said, typically either the system call is implemented, in this case it goes to the PM, okay, process manager, either fork is going to be completely implemented by the process manager or it is going to ask the OS to do something for it. Okay, fork actually is the first system call that creates a new process in the system. Okay. Typically you will need some help from the OS to do this because you are going to allocate new memory for that process. Okay. So, you are going to also talk to them, the memory manager, you are going to talk to the OS. So, there is actually multiple steps involved, because fork is one of the more complex system calls you are implementing. Okay. So, essentially you are going to not only talk to the kernel, you are going to talk to some other system processes as well to collectively implement fork functionality. Okay. Here are all the steps that occur. You need to know the top few because the bottom ones you do not really actually need to know, but they exist, okay, in the pipeline. Okay. So, you are going to call fork. Okay. Every system call eventually uses an underlying call called syscall. Okay. That is the one that causes the trap. Okay. So, when you call syscall, okay, that causes a trap, it goes to the kernel. Okay. And then the code is actually there, which you do not really need to know. Okay. And then you are essentially going to use message passing to call the interrupt vector. Okay. That is the trap vector. Okay. And that trap vector will be in many cases architecture dependent, because that trap is an architecture specific feature. Okay. So, this is where that code is going to go into assembly code. Okay, so that's I386, which is Intel architecture. It's going to go into some assembly code where it's going to trap into the kernel. Okay, pass some arguments. Okay, in this case, you're passing one argument, which is the ID that you have to index into, and then you're going to continue execution of that code. Okay, several steps. Okay, but to implement a new system call, you are only going to focus on the top few because all the bottom few is common. Once you call this syscall, doesn't matter. Every system call has to call that function, and then everything else just goes through the microkernel. Okay, is that clear at a very high level? I haven't actually spoken about what fork does. Okay, we'll get back to that when we talk about process management, how a new process gets created. Okay, I'm going to show you a picture just to show this thing in a pictorial fashion. Your question?
Yeah, so we keep saying that the user processes can't basically make kernel calls, but they can make one kernel call, which is to send a message to other servers, you're saying, because it traps directly into the kernel and then sends a message from the kernel to the servers.
Right. Well, you are essentially calling, in this case, fork. Okay? Fork is going to be implemented as a library. Okay? Initially, that library is going to essentially do what you just said, which is going to cause a trap and whatnot. Okay? So that's basically what is happening. Okay? So here's a picture that's showing you all the various things that happen in fork. Again, the details of what fork does we'll get back to, okay, because it's creating a new process. But as you will see, what is happening is fork has essentially come to the process manager. Okay, the time is vertical here. Okay, you go to the process manager. Process manager actually calls the memory manager, says you need to create a process, allocate some memory. Okay, that is why now you essentially called a function that goes to another system process. Okay, so you got to understand that the system processes have to communicate in order to implement fork functionality. Okay, so this system call involves multiple system processes, as we'll see. So essentially, the memory manager is going to call the kernel and do some extra memory management stuff, which we'll get to as well. Essentially, it allocates a block of memory, okay, to this process. Okay, once that is done, the process manager is going to call sysfork, which goes into the kernel. Kernel allocates some new data structures for this process, and here's a new process. Let's give it a new process ID and whatnot. So that's what sysfork is going to do, which is why you need to go to the kernel in order to make changes to these data structures. Okay, so that's essentially the kernel call. Okay, so because you go to the microkernel, and once you're done, okay, you basically return, and you will see that in this case, okay, you have created a new process, okay, child process. So you are essentially going to return that fork to both the parent and the child. Okay, so this is one of the more complex system calls. Your lab is not going to ask you to do anything like this complex. You're going to do something much simpler, but you should know all the things that happen. So the high level things are a system call may involve communication with other system processes. So you go to one process, but that process might need to communicate with others to implement functionality. It may additionally need to call some kernel calls in the microkernel. Okay, so both of those things may be necessary in order to implement this functionality. Is this clear? Any questions on this? Okay. All right. So I already said something about system calls. So very quick things about kernel calls. So some system calls may require a kernel call to implement functionality, but there are some kernel calls that don't correspond to any system call. They are generic kernel calls that may be needed by other OS components. So for example, there are kernel calls that are device driver specific, that are never going to be invoked directly from user space because device drivers need them to implement certain functionality. Okay, there's an example here of dev.io that's basically used a kernel call that is used to communicate with hardware. Okay, device drivers make these calls, not system processes, not user processes, and things of that sort. Okay, so some kernel calls specific to device drivers, some kernel calls specific to system calls. There are still other kernel calls that are just implementing IPC primitives, send a message, receive a message, that just provide general purpose IPC, okay, that are implemented by the microkernel. So this is by and large the collection of kernel calls you are going to find, okay, within Minix. Okay. Okay. So the thing to keep in mind is the reason I mentioned user processes cannot invoke kernel calls is that you can actually set permissions on who can invoke what calls. Okay. That is done in a file called system.conf, which I showed you last time if you remember. Okay. I am going to show it to you again, because you will have to change that file at some point in the lab. Okay, let me start VirtualBox. Okay. Okay, so this is the file that you need to keep in mind. This is what controls which system process can make what kinds of kernel calls, what kind of IPCs and things of that sort. Okay. So I encourage that you go look at this file. You are going to actually modify it at some point during the lab. So you will see that that's the reincarnation server. It says IPC all, which means it can make IPCs to any other OS component. There are no restrictions. Okay. It is allowed to make all kernel calls. So system call is all. These are the calls it makes to the memory manager. Only those calls are allowed, nothing else. So you can say either all, or there are, if you actually read the man page for system.conf, it specifies how you can set these permissions. Okay. So I'll show you some other things. So you don't really need to worry about scheduling and all those entries at the moment, but we can look at some other processes. So here's the process manager. Okay. So it says again it can make all IPC calls, all system calls. Here are some VM calls that are allowed and things of that sort. And there are some that are more restricted than all. If you go through this, okay. So here is the scheduler. Okay. So you will see that it only says that some IPC calls are allowed, not all. Okay. It can only make some basic calls to the memory manager, which is called the VM, and so on. Okay. So that allows you to determine, or allows the kernel to determine what is allowed, what is not allowed. Okay. And then if you do system.conf for man, okay, you will essentially see some documentation that tells you how you can add entries to that file and so on. Okay. Yes, question. Okay, that's a good question. I think they defined that. So you will see that there are some options, all, basic, none, or you actually specify a list. Okay. So basic only allows basic kernel calls. See that list to say what is included in the basic calls. Okay. So basically it's a smaller group than all. That's all it means. And that list of what is allowed is specified there. Okay. But you can just say these are the calls and just list the calls, and that's the only thing that will be allowed if you don't like either all, basic, or none. Okay. All right. So the reason I mention all this is because you are going to start touching all this in your lab, okay, in the lab assignment. Okay. So let's go back to the lecture slides. Okay. So kernel calls done. Okay. So now I'm going to spend the remaining whatever time we have talking about the lab, and then you should of course ask whatever questions you want, so we can make sure you understand what is expected and things of that sort. Okay. Yes. Yeah. Yes. Yes, you can make whatever groups you want. Right. So that's basically it's a permission file. You can set those are the default permissions that Minix ships with. You can change those permissions, and then based on what you changed, more things will be allowed or less things will be allowed. Okay. Normally, only thing you will change is you will actually add an entry for your own server and decide what to allocate. You don't have to change any of those things, but just something you need to know. Okay. So the first lab, okay, is going to implement a system call, implement a kernel call, implement a new system process. Okay. So you basically understand how all of these things work. All right. So it's going to be handed out on GitHub just as we handed out lab 0. We're going to hand out lab 1, and you are going, this time you actually have to turn things in, because last time we didn't have to turn anything in. So all your code has to come in through GitHub. Okay. Make sure that you commit on a regular basis. Don't just do everything and then commit at the end. We want to see how you developed your code and so on. Okay. Just as you do it for any source code repository, we expect that you are going to use it as a regular repository, not just something you turn things in at the end. All right. So, this is kernel programming. Okay. So, you are going to make mistakes and crash your kernels and things of that sort. Okay. So, you got to understand that is going to happen, and we will try to help you as much as possible. Yes. What's the question? Who will grade it? Okay. So, the grading will be done by the TA and to some degree me, but what you will have to do, one of the things you will have to do is sign up for a 15-minute slot, come and show what you did to the TA, because if only half of your code works, we can't compile your kernel, we cannot grade it. It's not like you're writing a user level program. So we're expecting that you will come and show what works, what doesn't work, and so on. Of course, you're going to turn in code, we'll look at that also. Okay. So it will be graded through a combination of a short one-on-one slot, well, two-on-one, because groups of two slot where you present what you did, and then we look at your code and grade it. Okay. But the other thing is that you should always feel free to go to office hours and ask for help. Okay. If something is not working, nobody has shown up for any office hours yet. Okay. I'm assuming that will change now that you might actually need some help. So please use that resource as well. Okay. Should you want more help, we can add more office hours time. At the moment, we have 3 or 4 slots, but it is not getting used. All right. So keep that in mind. Okay. So you are going to, as I said, kernel may not work, things may not boot. Don't panic. Okay. That's the motto for the class. Your kernel may panic, but you shouldn't come ask for help. Okay. So what we have done to help you, because most of you probably have not modified a kernel yet, maybe the first time you are touching a kernel. So we'll start with a very gentle introduction, okay, more like a guided tour, and then we'll have you do something. Okay. So the lab has 2 parts. Okay. First part is very scripted. Okay. You could just not know anything about those. You could just give those instructions to any person you find at UMass, and they would just execute those, and the lab will be done. Okay, because we told everything what you need to do, but that's not the goal. The goal is we told those steps to you, so you understand what is involved in implementing system calls and kernel calls, and through that you understand what the process is, and then in part 2 you actually do something. Okay. So this way you don't have to go and try to figure things out yourself, because the OS has some documentation. It's not that well documented. Okay, you got to really dig deep sometimes, figure out what is going on or what has to change. So we listed those steps for you already. Okay, all the main steps you have to perform are already told to you. So once you do the more scripted version, you understand how things work, and then you go and do your own thing. Okay, which is better than us just telling you go write the system call and then you got to figure everything, which I think is not easy in any operating systems world. Okay. So I'm going to show you part 1, and then we'll talk about part 2. Okay. So that's lab 1, which is going to be given to you. Okay. So we have a samples directory in there, which is where you will actually do part 1, where we have actually told you how things work. Okay. So there's a sample implementation of, not implementation, set of steps of how to implement a sample kernel call, a sample system call, and a process. And I'll just show you each of those, so you can have some sense of what is going on. Okay. So let's start with the system call. Okay. So if you go read the README file, it's actually going to tell you everything. So this system call is essentially going to do it's a print message call. It doesn't do anything. It just invokes a system process and has this print a message. Okay, dummy system call. But all the steps that you have to do are actually the more important things here. Okay, so first thing you are going to do is define a new prototype. Okay, so you basically, all of the system calls have a do prefix. Okay, so you'll say do print message. That's going to say that's a new system call. It has to go in that file there. Okay, then you got to allocate a new entry for that function. Okay, you got to find a number that's not in use. You can't just take some other system call ID and put your own. So there are a couple of unused entries. One is number 69. I think 70 is also unused. So you can use those two. Okay. So this one we just suggest you can just use 69 as is shown here. Okay. So that's essentially unused. So you're going to change that. Okay. And instead say I'm going to implement the system call, and now it has an ID 69. Okay. You defined that number. You're going to also go in that header file and do the same thing. Okay. Now that's just declaring that you have a new system call. You got to write code for it. Okay. So you're going to just write the code. It's essentially a one-line function, because these are all in this case very simple. Okay. So you're just going to have a do print message, all it is, and that's where you add the code for your system call. Okay. So in this case just prints a string, doesn't do anything interesting. Okay. So then you have to compile it, okay, and then test it. Okay. Typically you want to have a user library that can invoke it, okay, which makes it easier for user level programs to do it. So here is a simple implementation of a user library that we also showed you what to do. Okay. So essentially you are going to just write that code that is mentioned there, and then write a test program. Okay. So that's essentially going to get you. So you got to do all this and make sure it works. Okay. So then, so that's the first part. Any questions on that part? Okay. Okay. So here is your kernel call. Okay. The previous one we didn't actually go. So we essentially invoked I think it was the, let me check, it was the process manager or the memory manager. So that system call was handled by an existing system component, which, okay, so it goes to the file server. So that system call essentially goes to the file server. So the file server actually executed that call for you. Okay. So you didn't have to implement a new system component. Okay. And all that code was just in there. Okay. Here is the kernel call. Okay. So in this case we are going to take that same system call, but now actually go into the kernel to execute it. Same print message. Okay. So there are more steps. Okay. So you are going to create an implementation of the kernel call, okay, and then do some extra steps to declare that to the kernel, saying here's a new kernel call. Okay. And then you're going to call a mapping between the kernel function and the system call, because the system call is invoking kernel service rather than being implemented in the file server. Okay. So you're going to do all of that. Okay. There's plenty of text there, you need to read all that. Okay. And then you're going to also call a kernel task, or not a kernel task, excuse me. You're going to call the system task that needs to now execute that. Okay. The system task, if you remember, is the component of the microkernel that implements all system calls or kernel calls. Okay. So here is the picture. This one, okay, this picture. Okay. So that kernel call implementation is going to go there essentially. Okay. That system call that we implemented in the first part essentially just went there. Okay. And it was executed just by that process. The kernel call requires that that system call now call some code here, and that is where you are going to essentially print that message. Okay. Okay. So all of that is spelt out here. You make a library, etc. Okay. The other thing you got to do here is to add that kernel call to the that system.conf, because remember you specify what kernel calls are accessible to what process. So you got to add some more entries to give permission, and then you're done. Okay. So you will say here this for file server process can actually now also call that kernel function that I just added. So it is allowed to make that kernel, because by definition it is not allowed to do all. It has a smaller list. If that was all, you would not have to add that entry. Okay. So we have to figure out all this. Nothing is documented anywhere. So we spelt it out for you. Any questions here? Okay. So that's part part 1, step 2. Okay. The third step is to now write a server process, okay, that's essentially going to be a new system component. Okay. All server processes, the way they are implemented is they just sit in an infinite while loop waiting for some user process to invoke services or some other system process to invoke services. Okay. So, essentially a loop that is just sitting there and waiting for requests, processing the request, sending back replies. Okay. So, again we have a prototype for you. So, you just write a main and essentially it is a standalone process, remember. So, it just looks like a user level process. So, your main function where you write this code which sits in a loop and you write whatever functionality you want in there. Okay. And then you have to tell the kernel that I have a new system process. So, there are some steps to tell my Minix kernel saying here is yet another process, okay, that we implemented. We call it the my server process. Okay. So, again if you go through these steps, it will tell you all of the things needed. So, you need to tell the kernel, you need to tell the reincarnation server, because these are the components that need to know what system processes exist in the system. So, they can start them, they can stop them, all of those things happen. Okay. So, once you do all of that, you will be done. You will have a process that implements this functionality and makes the kernel call. Okay. So, we have given you all the steps needed in this case to do part 1. Okay. Once you go through this, you will essentially get a skeleton of all the things you have to do. Okay. Part 2 is essentially to now write your own system call and a server process. It is not very complicated. Okay. We just made it very simple. There are only 2 system calls to write, add and multiply. Okay. So, basically you will have a calculator process which is now a system process. It implements 2 services, an add service and a multiply service. Okay. We will assume that add service can be handled in user space. That means it is only a system call. Okay. When it comes to that process, it takes the arguments, it sums them up and returns the result. Okay. We will assume that multiply process cannot be done in user space, you have to call kernel call. Okay. So, you are going to implement a kernel call to do multiplication. Okay. Take 2 argument, multiply, return. Okay. So, if you do all this, then I think you learned how to write a user level process, that is an OS component, okay, implement a trivial, okay, really trivial system calls, but the process that is more involved than the code that you are going to write. Okay, the code will be very little in some sense, maybe less than 20 lines, but where you go make changes is when you learn how things work. Okay. So, that is the lab. Okay. This one is somewhat straightforward, because we told you everything you need to do. Okay. Things will still go wrong, I am pretty sure. So, you should come and ask for help. Okay. But subsequent labs will require that you will try to now figure things out, more things on your own. In this case, we kind of spelled everything for you, because presumably is the first time you are doing kernel programming. Okay. So, you can do this in groups of 2. You do not have to, but you can. Okay. So, you decide whether you want to do this as an individual lab or a group. Okay. And then once you form your group, okay, if you do form your group, you have to do one thing. Okay. When we send you a GitHub invitation, okay, if both people in the group accept that invitation, it will create 2 repositories. That is not what you want to do. Okay. You want to have 1 repository per group. Okay. So, if you have a group, only 1 person should accept that invitation, and once the GitHub repo is created, we will allow you to add the other person as a collaborator on that group. Okay. So, the repo will belong to 1 person in the group, and the other person will have all the access to check in, check out code. Okay. Do not accept the invitation twice, otherwise you will have 2 repos. Okay. That will not be the right thing to do. Okay. If you are doing individual, of course, there is no problem. You just accept the invitation, you get your own cloned repository. Okay. So, are there questions? 2 weeks, okay, is what we think is reasonable. Okay. Do not wait until the last minute. This is not the kind of stuff that gets done at the last minute. Okay. I would strongly suggest that you finish the scripted part soon, okay, and then start the real thing, and then you have essentially 2 weeks to do the real assignment. If you start the scripted part late, then you will not have enough time if something goes wrong. Yes, question?
Just kind of bringing it back to the class lecture. The system
The system.conf file defines permissions for the servers. Okay, not user processes, only system components. Yes.
Is there a similar file for like drivers and things, or do they just get all?
Okay. Question is there a similar file for drivers? It's the same file. There's only one file that has everything, and you can actually verify that by going here. If you keep scrolling down, eventually you will hit driver. So here are some file systems also where you, so these are also processes. That's the ext2 file server. If you see what I just scrolled past, that was the NTFS file server, so on. Keep scrolling down, eventually you hit some drivers. Here are some drivers, the floppy disk driver, and so on and so forth. Okay. So this is where you can even say which interrupts can be received by what system call, I mean what driver, and so on. Okay, that is where there are lots of entries there. But yes, that is how things work. We'll get to drivers in a little while. Okay. Any other questions? Yes.
Are there any techniques to sort of decrease the compilation time of the kernel, or like do some modular level, any techniques generally which developers follow?
So the question is there anything you can do to decrease the compilation? If you do make, it shouldn't compile everything again, right? It all automatically does incremental build. So once you do make, if you keep, unless you do make clean, which then goes out and wipes out all your object files, hopefully it shouldn't. Okay, it should only compile the 2 files. As it is, Minix only takes minutes. Okay, if this was a Linux assignment, prepare for several hours of compilation. Okay, so every time you make it, well, it should be every time. If it's incremental, it should take quick. I mean, it should be quick, but yeah, it takes a while to compile. Okay. Now, a few other things to keep in mind. I mean, before you make some mistakes, don't actually edit code inside the Minix VM, because if you crash it and it doesn't come back, your code is gone. Okay, it's better because everything is connected to Git, and as far as I know, there is no Git client for Minix. If you find one, let us know. Okay, but we couldn't actually find anything. So separate the build and the dev environment. Okay. The dev is where you write your code. That should be your laptop, and you just connect to Git and do whatever you want in your favorite browser and whatnot. Okay. And then all you need to really do is take those files and just use SCP or SFTP and just paste it in the source directory. Okay. It can override those files because the master files are on your machine. Just paste it, just run make. So just build inside the VM, don't develop inside the VM. Much better. Okay, because even if you develop inside the VM, you cannot check it into Git. You have to pull it out and then check it. It's somewhat painful, but that's the way it is. We couldn't find an easier workflow. So our recommendation is you keep your code outside because it's safer to begin with. Okay, even if you crash your machine, nothing is lost. If there was Git inside the machine, of course, you could keep checking it to Git. So even if a machine crash, your code is safe. But there is, to our knowledge, no Git client. Okay, but if you find someone, just let us know, as I said. Okay, so keep some of these things in mind. Yes.
What are some good debugging practices for developers?
Okay, good. So good debugging practice. So we will get to some of these. Okay, so kernel debugging is a hard problem. Okay, there are debugging methods for the kernel. Unfortunately, Minix is somewhat primitive in that regard. First line of defense is print message, which is not the best approach, but that is what you do. Okay, even for more sophisticated kernels. Okay, you can certainly try that. Okay, now kernel, there is ways to do kernel debugging. You can actually attach a GDB to the kernel, but the only problem is the GDB can't be running on the same OS that you are trying to debug. Okay, so there's something called remote GDB, where GDB is running on one machine, and then you are connecting, in this case, to a VM and trying to debug it from the outside. Okay, the only problem is because we said VirtualBox does not have a GDB stub. Okay, so you cannot actually debug any kernel inside virtual. This is nothing to do with Minix actually. If you are actually using KVM and QEMU, you can actually connect GDB because it has GDB stub. Okay, so if this becomes a problem, then we will have people switch to either a free version of VMware, which has a GDB stub, so you can actually debug Minix or any kernel. You can actually do stepping through each line of code and debug it as if it was any other process. Okay, but we said VirtualBox, we didn't actually know there was no GDB stub, So after spending a lot of time, we realize it's not going to work. Okay? So we will. There are other things you can do with VirtualBox. There's a hardware level debugger, but that really requires you to understand assembly code. That's not what you really want to do here. Okay? So we are still trying to figure out an easy way by which you can do debugging. This hopefully shouldn't take a lot of debugging because there's not a whole lot of code. Most of it is probably going to be configuration errors rather than coding errors. You forgot to put some entry in or didn't give the right permission. That's the more likely cause of the problem rather than there's an error in your add function, which is very hard to believe. Right? So I don't think that's what is going to happen. So, but we'll get to debugging. We are still trying to figure out because it requires us to switch to a different virtualization platform that has better GDB support. Unfortunately, VirtualBox doesn't cut it for kernel debugging. Yes?
I'm not sure about 3.2.1 because I originally installed Minix 3.3.
Yeah.
But it has a Git client.
Okay. So 3.2.1 does not have one, but we'll check. If you can send me a note where you found it, we'll see if we can compile it for 3.2.1.
Yeah, it took a lot of reading mailing lists.
Yes. Yeah. So just let us know if you found it. But I mean, still, we would not recommend. First of all, there is no good editor. You have to essentially have an editor with SFTP support to even edit code. So you may as well not do it inside is our recommendation. But just let us know if somebody needs a Git client, we can put it out there. Okay. Yes.
Can any of the servers trigger kernel panics, or is it just like
Yes. So the good thing about Minix is that only Minix microkernel will cause kernel panics. System process crash does not cause kernel panic. Okay? So you will silently see a process crash. The reincarnation server will silently bring it back up because it's checking if system process crashes and then it restarts it, and you may not know. If the bug persists, it will keep crashing. Okay? But yeah, you won't see a kernel panic. That's a good part about Minix. Okay? But you may still when you do a kernel call programming, still crash the kernel. Okay, but yeah, most of this is going to be user land code. Yes, any other question? So debugging we will get back. Okay, we don't have good answer because we chose the wrong platform. Any other questions? Okay, so we'll stop here. Start the lab early. Okay, don't wait until the last minute.
I found this on the Minix 3 wiki.
Recording.
They